Hi everybody, welcome back. What we're going to do today is continue talking about hypothesis testing, but now we're going to focus on section 9.2. In the previous section, we talked about the basic structure for a hypothesis test. Now we're going to put everything together and we're going to do our first hypothesis test with means. And specifically, we're going to talk about one-tailed tests and two-tailed tests and the differences between them. And we're just going to really learn how to put it all together, everything that we learned about z-scores and computing probability, so that we can determine how likely it is that we found our data by chance. If we're able to rule out chance, we're able to say that we have statistically significant results. By the end of our discussion, you should have a good sense of what that means. Let's jump right in. In previous examples, someone was computing the necessary probabilities for us, and then we were making decisions about having statistically significant results or not. But in the real world, we have to compute our own probabilities, which in reality is easy because we've learned some tricks. We've learned how to take our data, transform it into a z-score, and then look up those probabilities in a table. We'll be able to look up those probabilities and determine if we have achieved statistical significance. And our professions tell us how much evidence we actually need. They tell us what significance level is necessary for us to have statistically significant results. So it's a little bit rude, I guess, because we don't have much of a say in that matter. For example, in psych and in nursing, the probability of finding our results just by chance must be less than 5% for us to say we have statistically significant results. But in medical research, as I've mentioned previously, we need more evidence. We need to rule out chance at an even greater level. And in that case, we have to prove that our results would happen by chance less than 1% of the time for us to rule out chance as a reasonable explanation and conclude that we have statistically significant results. So we need even more evidence in those situations. So we're going to discuss how we can determine if we have those significant results by comparing our results to some critical values, some critical z-values. And those values are going to show us exactly how much evidence we need for any given alpha level, like 0.05 or 0.01. That alpha level is the significance level that we're working with. Let's just jump into an example and you'll see what I'm talking about. We learned that left and right-tailed tests are known as one-tailed hypothesis tests. And the thing that makes them unique is that researchers typically in those cases have very clear predictions for the directions of the results. So the probability that we compute is only on one side of that sampling distribution because the researchers are predicting that the results can only go in one direction. Here's an example. Let's say that Columbia University states that their graduating students earn on average $39,000. That would be the null hypothesis, that the salary for these students equals $39,000. But let's say that some researcher or some independent research firm believes that that's not the case and that that's an overinflated value and that the graduates actually earn less than $39,000. Well, if we structured it this way, this would be an example of a one-tailed test. We're predicting here clearly that the population average salary for those Columbia students is less than $39,000. Now, we will be able to learn about that population of students by collecting evidence, collecting data from a sample of those students. And let's say that the researchers testing this collected data from a sample and they found that the sample mean, X bar, was equal to $37,000. Well, now we need to compare that evidence to something. We clearly see a difference between $39,000 above and this $37,000 right here. There's a difference. But is that the type of difference we would just expect by chance? Is that a large enough difference to rule out chance? And here's how we'll be able to answer that question. We're going to consult a distribution of all possible sample means. That's why we had to talk about that earlier. So this line right here is representing the distribution of sample means if the null hypothesis is true. And this distribution of sample means will always represent all possible sample means if this null hypothesis is true. And what that simply means is we're expecting that the average score for the population is equal to $39,000. But we realize when we collect data from samples, not every sample is going to give us exactly that value. Not every sample exactly represents the true population mean. So sometimes we're going to find a sample mean that's a little higher. Sometimes we'll find a sample mean that's a little lower. So for example, think about this sample mean right here. It's not very far away from $39,000. So it says that this sample mean is near the peak. It's near the peak or the middle of this distribution. And these means are fairly likely. They're likely to occur just by chance. Therefore, it doesn't give us much reason to reject the null hypothesis that the population mean really is $39,000. Because we would expect some means to be less than $39,000 even if the true population mean equals $39,000. But think about this mean right over here. Here's a sample mean that's very different from $39,000. This is quite a bit lower. If the true population mean is $39,000, it's very rare that we would find a sample mean this low just by chance. So the bottom line is when we say we have statistically significant results, we say the probability of finding this data just by chance is very, very low. So we effectively rule out chance, and then we conclude that our null hypothesis is not correct, and we take on the alternative. Well, the question is, how much evidence do we need? How far out does this mean need to be for us to say it's very unlikely to occur just by chance? So we need to figure out where is this critical region, this highlighted part in green here we call a critical region or a rejection zone. Well, what we're going to do is figure out a way to use our z-table to find where those critical rejection zones are. And then we will figure out where our mean is. So what we're going to need to do is convert our sample mean into a z-score. That's easy. We've done that several times already. We've got a simple formula for converting a sample mean into a z-score. Once we convert that into a z-score, then we can figure out where exactly in this distribution that score is. So now we have a distribution of sample means that's been converted into z-scores. So the population mean would be equivalent to a z-score of 0. It's right there in the middle. And now we're able to figure out where in this distribution is this particular mean of 37,000, because we'll convert it to a z-score and then we'll know exactly where it is. Then we'll be able to figure out where these critical values are. And over here, if we're looking at the 0.05 level, what we're saying is we want to find where there's 5% of the distribution right over here. What point cuts off where there's 5% left in the distribution? Well, according to this graphic, it says that this value right here of negative 1.645 cuts off where we have 5% of the distribution left right there. Let's try to figure out where we found that from. I'm going to show you here the z-table that we looked at in chapter 5. And you'll recall this shows us percentiles. So it shows us the percentage left in a distribution below it at any given point. So right there in the middle, we have a z-score of 0. How much of the distribution is to the left of 0 below a z-score of 0? 50%. So now I want to figure out, I'm going to just start looking down these percentage columns. Where does it show me 5% left in the distribution? And what z-score is that associated with? Because that's going to show me the critical value, the critical z-value that marks off where there's 5% left in the distribution. Well, let's find around the closest thing. Here I see about 5.5%. There's about 4.5%. Well, somewhere between these two is that critical value that marks off 5% in the distribution. And now we can see where that number comes from that we saw in the previous slide. So we see it should be somewhere between 1.6, negative 1.6, and negative 1.7. So going back to that slide, we see here negative 1.645. Now we understand where that comes from. This is going to show where there's 5% left in the distribution right here. So if we transform $37,000 into a z-score and we find it's in this critical region, we know we would only expect to find that sample mean less than 5% of the time just by chance. So that would give us enough evidence to rule out our null hypothesis. But if we transform this into a z-score and we find that it's not in the critical region, then we say that's exactly the type of sample mean we would expect to find just by chance. So even if the true population mean is $39,000, I'd expect to find a mean right here quite often just by chance. Then we do not have statistically significant results. All right, well, that's it in a nutshell. Let's start putting it all together. Of course, when we're talking about that critical region, sampling distributions are symmetrical. So if the critical region for a left-tailed test will be marked off at a z-score of negative 1.645, the critical region, or this rejection zone here, for a right tail test will be marked off at positive 1.645. So that's really easy. And of course, like on exams and when we're working on things in class, I'll always provide you with some type of table so that we can find that value. So this table summarizes what we need to know. For a left tail test, we find that for an alpha of 0.05, we will reject the null hypothesis if that standard score, that z-score, is less than or equal to negative 1.645. If we're doing a right tail test, then that critical value for an alpha of 0.05 is marked off at 1.645. So if our z value is greater than or equal to 1.645, we will reject the null hypothesis. All we're seeing in here is it's telling us if our sample mean, when we transform it into a z-score, is in this region, we reject the null hypothesis and conclude we have statistically significant results. If our sample mean is in this region, we reject the null hypothesis, conclude we have statistically significant results. Now, if we're using an alpha of 0.01, where we need more evidence, now that critical value will be marked off at negative 2.33 and positive 2.33. So you see it's pushed out even more. So that's only showing 1% of the most extreme sample means. So if our sample mean, when we transform it into a z-score, is greater than 2.33 or less than negative 2.33, we would have statistically significant results at the 0.01 level. All right, well, I think we've talked about it enough. Now it's time to just start walking through some examples and put it all together. So we will revisit some of the examples that we talked about in 9.1, where we were just setting up the hypotheses. So that part should be pretty easy for us at this point. And that's always step one, to set up our hypotheses. So let's remind ourselves of this situation. Columbia College claims the mean starting salary of its graduates is $39,000. An independent organization suspects that that is an exaggeration. They select a sample of 100 graduates and find the mean salary equals $37,000. We want to test to see if there are statistically significant differences between these values using an alpha of 0.05. So let's set up our hypotheses. Remember, we always have two competing hypotheses, a null hypothesis and an alternative hypothesis. Our null hypothesis is stating that the population mean salary for those Columbia students is $39,000. Okay? The competing hypothesis, or alternative hypothesis, is that the population mean salary for those Columbia students is less than $39,000. So this alternative is saying the population mean is less than what is being claimed, $39,000. So step two in any research study now is where we would collect some evidence. And here in this paragraph, we have information about the evidence that was collected. 100 graduates were sampled, and we found that the mean salary was equal to $37,000. So the mean salary, X bar, is equal to $37,000. And let's just assume in this case that the population standard deviation for those salaries is equal to $6,150. So that's just a value that I have. I'll always give you this basic information. And we're just going to assume that this population standard deviation holds true. So now let's compute the probability based on the assumption that our null hypothesis is true. This is what we're always doing. We're computing the probability of finding this data just by chance based on our assumption that the true population mean equals 39,000. So in other words, where in this distribution of z-scores is our sample mean of $37,000? We know right here in the middle is that population mean of $39,000. If we were to transform it into a z-score, it would equal a z-score of 0 because it's right there at the mean. We want to figure out now, where is that mean of $37,000? Is it a mean somewhere around here, which means it's quite likely we would expect to find it just by chance? Or is it a mean that would be in here, which is very unlikely to be found just by chance? Well, we need to transform this into a z-score, and this is of course how we do that. First, we're going to need to compute the standard error of the mean. So we'll use this formula right in here. So we take that population standard deviation, 6,150, and we divide by the square root of the sample size. Of course, the square root of 100 equals 10, and we're left with 6,150 divided by 10, which is going to equal 615. Once we compute that standard error, now we have a sense of how much these sample means differ from the true population mean just by chance. That's what standard error measures, how much the sample means differ from the true population mean just by chance. So it's a measurement of variability from one sample mean to the next. Now that we know that value, we can plug it in down here to our formula for Z. So we take our sample mean, 37,000, we subtract that population mean, which is based on the null hypothesis of $39,000, and then we divide by our standard error of the mean. So we see differences here of about $2,000 relative to the differences between means that we expect just by chance. And we find a Z value of negative 3.25. And we can verify that real quickly with our calculator. If we take 2,000 and then we make that negative, we can then divide by 615 and we find a value of negative 3.25. All right. So now we want to figure out where is negative 3.25, because that shows us exactly where $37,000 is in this distribution, because negative 3.25 is just another way of expressing $37,000 as a mean. Well, here's a z-score of 0. Here's where our critical region starts at negative 1.645. Negative 3 is clearly way over here. It's in this critical region. It's in this rejection zone. If it's in the rejection zone, it means we have enough evidence to reject the null hypothesis and conclude that we have statistically significant results. Because it's very, very unlikely that we would find this mean of $37,000 just by chance if the true population mean is equal to $39,000. So we have enough evidence to conclude that the population mean, the true population mean, is less than $39,000. So let's formalize our results in step 4. There are a couple different ways that we want to do it. So first of all, just to summarize, our Z value of negative 3.25 exceeds that critical value of negative 1.645. So it's more extreme than that value. You just want to see it in terms of being in this critical region or rejection zone. So the probability of finding this result just by chance is less than 5%. All the sample means in this critical region here occur less than 5% of the time. They're very, very unlikely to be true if the null hypothesis is true. They're very, very unlikely to occur if the null hypothesis is true. So the result is statistically significant at the 0.05 level. So finally, we will reject the null hypothesis and conclude that the population mean salary for the Columbia students is less than $39,000. So we're rejecting this null hypothesis. We have enough evidence now to rule it out, and we'll take on the alternative that the population mean salary for the Columbia students is less than $39,000. All right, well, there's one example of a complete hypothesis test where we found that we had statistically significant results. We effectively ruled out chance as a viable explanation for our results. The difference that we found between 39,000 and 37,000 is not likely to occur by chance. Let's look at this next example. We'll speed up the pace just a little bit because you have a good sense of the background now, I hope. A rental car manager suspects that his fleet travels more than 12,000 miles a year. He sampled 225 cars from his fleet and found that the sample mean was equal to 12,375 miles driven per year. So that's higher than 12,000. Is this the type of difference we would expect just by chance? Or is it very unlikely that we would find a difference between those numbers just by chance? Well, we're going to test that with an alpha of 0.05. And again, we're going to set this up like it is a one-tailed test. In this case, the manager is suspecting that his fleet travels more than 12,000 miles. So on that distribution, when you think about a number line, 12,375 is on the right side of 12,000. So this would be a right-tailed test. So our null hypothesis is that there are no differences, right? And it's that the status quo is true, and that is that the fleet travels about 12,000 miles a year. Well, the alternative is that the mean miles for the fleet, the population mean miles for the fleet, is greater than 12,000 miles per year. So we have these two competing hypotheses. The null hypothesis is always based on no effect, no differences. If the industry standard is 12,000 miles a year, then we need to just believe you're traveling 12,000 miles a year unless we can rule that out and conclude that the alternative is true. So now we're going to collect some evidence, and we have some evidence that I've provided you. So from these 225 cars, we found that the sample mean miles driven is equal to 12,375, and let's just assume that the standard deviation is equal to 2,415 miles. So I'm just giving you that number so that we have all the information that we need. Let's now compute the probability of finding that data based on our assumption that the null hypothesis is true. Remember, we are always looking for the probability of finding that data just by chance based on our assumption that the null hypothesis is true. So we look at that distribution of sample means, and this distribution of sample means has been transformed into a z distribution. So right there in the middle, it represents 12,000 miles, but of course that mean transforms into a z-score of 0. It's right there in the middle. It's the population mean based on the null hypothesis being true. So we would expect, some variability from 12,000. Well, we found a sample mean of 12,375. Is that the type of sample mean that we would expect quite often just by chance? In other words, when we transform it into a z-score, is it going to be a z-score pretty close to 0, somewhere around here? Or is it going to be a z-score that reaches into this critical region? Is that z-score going to be more extreme than 1.645? Because if it is, this shows sample means that we would not expect to find very often just by chance. Well, let's figure out where it is. Let's transform 12,375 into a z-score. First thing we need to do is compute our standard error. Standard error is needed to compute z. So we compute the standard error of the mean using this formula. We take that standard deviation, 2,415, divide by the square root of the sample size. In this case, there are 225 cars in the sample, so we take the square root of 225. So that leaves us with 2,415 divided by 15. Let's just verify that this comes out to 161. We'll use our calculator. 2,415 divided by 15 equals 161. All right, so our standard error equals 161. What that tells us is that the sample means differ from the true population mean on average by about 161 miles. By about 161 miles on average, these means differ from one another. So now that we know the variability between sample means that we would expect just by chance, we can plug that into our z formula. So here we're going to look at actual differences that we see between our sample mean and the hypothesized population mean. So these are actual differences that we observe over differences between means we expect just by chance. That leaves us with 375 over 161. And again, just to verify that, we can take 375, divide by 161, and we find a z-score of 2.33. Looks like it rounds off to 2.33. All right, well, now that mean, 12,375, has been transformed into a z-score, 2.33, we know exactly where it is in this distribution. So 2.33 is somewhere right around here. This is the type of sample mean we would not expect very often just by chance. We would expect to find a sample mean like this just 5% of the time or less just by chance. Well, that meets our cutoff point. We're using an alpha of 0.05. So that is rare enough that it casts doubt on this null hypothesis. We have enough evidence to reject it and conclude that the alternative is more likely to be correct, that the population mean number of miles driven for the fleet is greater than 12,000. Let's go ahead and formalize that in step 4. And be sure that you're getting down how I write this out in this formal way because it'll help you interpret the results come test time. So we found that z equals 2.33 clearly exceeds the critical value of 1.645. So the probability of finding this result by chance is less than 5%. In other words, the result is statistically significant at the 0.05 level. So if we found that our sample mean is beyond the critical value, in the critical region, in this rejection zone as we call it, we know that we will reject the null hypothesis. And if we're going to reject this null hypothesis, we're going to then take on the alternative hypothesis and conclude that the population mean mileage for the fleet is greater than 12,000 miles. So do you see what we're doing? We're using this sample data to learn about the true population mean. And because this sample mean was larger than 12,000, and because it was so unlikely to find that type of difference just by chance, we're able to conclude that the true population mean miles driven for that fleet is greater than 12,000. So with inferential statistics, we use sample data to learn about the populations they represent. Let's go through some more information here. We've been dealing with one-tailed tests. Well, in reality, most tests are two-tailed tests. And the reason that most tests are two-tailed tests is because we usually don't really know exactly which way our results are going to go. I mean, in the case that we just talked about, it's possible, just as we're thinking about it, that this person's fleet of cars travels less than 12,000 miles in a year. Of course, it's possible that the fleet travels more than 12,000 miles in a year. The results could go in either direction. Well, if theoretically the results can go in either direction, most researchers will conduct a two-tailed test. And what that does is it leaves open the possibility that we have statistically significant results in either direction, where the true population mean is either less than the proposed value or higher than the proposed value. Now, the only thing that differs here is if we're using an alpha of 0.05, for example, when we're doing a two-tailed test, we have to take that 5%, the most extreme 5% of the means, and distribute it between these two tails. So we distribute it equally. So that would mean we would have about 2.5% of the most extreme sample means right over here, and about 2.5% right here. So if we're doing a two-tailed test, I need to find the critical value that shows me where there's about 2.5% left in the tail. Let's consult our Z table just to get a sense of where that is. So I want to find where it says about 2.5% and find the closest thing. Well, the critical value should be somewhere between -2 and -1.9, because this is showing where there's about 2% left in that distribution to the left-hand side. And of course, it's a symmetric distribution. So once we arrive at a Z value that we're happy with, that shows 2% left on the left tail, then we'll be able to use the positive Z value to show where there's 2% left in the right tail. So we know it should be a value between -1.9 and -2. So we can go back to our table, and you see that the value that we actually find is plus and minus 1.96. So 1.96 is right over here. That marks off where there's 2.5% left in the tail. And here we have 1.96 marking off where there's 2.5% left in the tail. And that would give us the critical regions necessary when we have an alpha level of 0.05. Now, if we're using an alpha level of 0.01, we have to take that 1% and divide it into two tails. So again, we're trying to figure out the critical regions for a two-tailed test. If I take that 1% and I divide it into both tails, I'm, according to this table, going to find a Z value somewhere around 2.575. Let's just see how we can kind of make sense of that. Let's look at our Z table again. So I want to find 1% divided in half would be 0.5%. Well, here is about 1%, about 0.8, 0.6, 0.4. So it's somewhere between these values. And the table had a value that was between these values. So we're just trying to make sense of where those critical values come from. A Z value between -2.6 and -2.5 is going to show us where there's about 0.5% of the means left in that distribution of sample means. So again, that's where we find the positive and negative 2.575. So if we transform our mean and it's in that critical region, we're going to have statistically significant results. Let's use that information to go through a couple examples of two-tailed tests. A drug company wants to be sure that its 500 milligram aspirin tablets really contain 500 milligrams of aspirin, as the average dose could be more or less. So they sample 100 tablets from some batch of tablets that they've created, and they find that the sample mean for those 100 tablets equals 501.5 milligrams. So there's more of the aspirin, more of the medication in each tablet, at least descriptively, than what they're looking for. But is this the type of difference that they would expect just by chance? Or is this difference so unlikely to be found by chance that we would say the true population mean is not equal to 500 milligrams, but it's actually equal to something closer than this? We're going to test with an alpha of 0.05, but in this case, we're going to do a two-tailed test. Well, our hypotheses are set up in a particular way for a two-tailed test. We're not predicting that our results are going to go in either direction. So our null hypothesis is going to state what we assumed all along, and that's that the population mean dosage equals 500 milligrams. But our alternative here, you're going to see, isn't going to predict a particular direction that differs from 500 milligrams. We're just simply predicting that the population mean dosage is something other than 500 milligrams. All right, so these are really very easy to set up when we're dealing with the two-tailed test. We will always have an equal to and non-equal to. So now we collect some evidence. So these people already did collect evidence. From 100 tablets, they computed the average amount of milligrams of aspirin in those tablets. And they found that the sample mean was equal to 501.5 milligrams. So there's our sample data, and let's just assume that the standard deviation equals 7 in this situation. Well, now we want to compute the probability of finding that sample mean just by chance if indeed the true population mean is equal to 500. So let's consult our distribution of sample means. We know we've got 0 right there in the middle. That coincides with the population mean of 500 milligrams. We need to figure out where's 501.5. Is it the type of mean that is pretty common to be found just by chance? Or is it the type of mean that's very unlikely to be found by chance? Because this value is greater than 500, we can see it's going to be on this side somewhere of the distribution. We just don't know if it's in the critical region or not. The only way we can figure out exactly where it goes is to transform that sample mean into a z-score. So the first thing we need to do is compute standard error of the mean. We will need that value for our z formula. We take the standard deviation of 7, divide by the square root of the sample size. There were 100 tablets in the sample. We're left with 7 divided by 10, which equals 0.7. So that shows us how much the sample means differ from the true population mean just by chance. So it's a measurement of how much error we would expect between those sample means just by chance. So now we look at how big are the differences that we've actually observed over those differences that we expect just by chance. Well, there's a difference of 501.5 compared to 500. There's a difference of 1.5 milligrams relative to 7 milligram differences that we would expect just by chance. That gives us finally a z-score of 2.14. We can verify that using our calculator. 1.5 divided by 0.7 equals 2.14. So 2.14 is just another way of expressing this mean of 501.5 milligrams. It shows us that that mean is 2.14 standard errors above the mean. Well, 2.14 is clearly in this critical region, otherwise known as a rejection zone. So it's the type of sample mean that we would not expect to find very often just by chance if the true population mean is equal to 500. So now we have enough evidence to doubt that this null hypothesis is correct. We have enough evidence because our mean is in that rejection zone to rule out the null hypothesis. So just to formalize things, our z of 2.14 exceeds the critical value of 1.96, so the probability of finding this result by chance is less than 0.05. In other words, the result is statistically significant at the 0.05 level. So we had enough evidence to reject this null hypothesis and take on the alternative and conclude that the population mean dosage is something other than 500 milligrams. And specifically, we found some evidence that it's higher than 500 milligrams. All right, I hope you're starting to get the hang of this. Let's go ahead and look at essentially the same example, but let's now use an alpha of 0.01. This is a study about a medicine. You would assume that this type of study might actually be published, if it were to be published, in a medical journal. And in medical journals, they require more evidence than what we typically find in a nursing journal or in a psych journal or a social work journal. They usually require an alpha of 0.01 in order to determine that you have statistically significant results. So more evidence is needed. We need to rule out chance at an even more extreme level. So let's see if in this case we would have statistically significant results. Well, our null hypothesis is going to be the same as what we had before, and so is our alternative. And the evidence that we have is the same. It's the same example. And in fact, when we compute the z-score, it's going to be the same value. The thing that differs here are the critical values that mark off where the critical regions begin and end. And you'll recall from the table that we looked at previously, when we have an alpha of 0.01, we need to take those critical regions and push them back even further. Because now we're going to take that 1% and divide it between these two tails. So it's no longer 5% divided by two tails, it's just 1% divided into two tails. So there's a 0.5% of the distribution listed right here and a 0.5% listed right here. So it makes sense that these critical values are now larger than negative and positive 1.96. Now they're boosted all the way up to 2.575 and negative 2.575. So again, right there in the middle, we have a z-score of 0. That represents 500 milligrams. Where is 501.5 milligrams? Is it the type of mean we would expect just by chance if the null hypothesis is true, or is it a very unlikely mean? Well, given our alpha of 0.01, 2.14 does not make it into that critical region. So if right here is a z-score of 0, 2.14 is, I don't know, somewhere right around here. It's clearly not in the critical region. So when we have this type of burden and we are required to show this much evidence, in this case, we can't do it. So we do not have enough evidence to reject the null hypothesis. We do not have enough evidence to say that we have statistically significant results. So what are we actually concluding? Well, let's walk through it. 2.14 does not exceed the critical value of 2.575, so the probability of finding this result by chance is greater than 1%. So using 0.01 as our criterion, we have not effectively ruled out chance. The result is not statistically significant at the 0.01 level. So if we fail to reject the null hypothesis, if we're failing to reject this, we're keeping it, we're retaining it. So I know the terminology is somewhat strange, but we are failing to reject it, which in other words says we're retaining it, we're keeping it. What we're concluding is that the population mean dosage for the aspirin is equal to 500 milligrams. That's exactly what this says. The population mean dosage for these tablets of aspirin is equal to 500 milligrams. The difference that we found here between 500 and 501.5 is the type of difference we would expect by chance if we're defining chance with an alpha level of 0.01. So we simply didn't have enough evidence now to say that we had any differences. Let's go through one more example. Researchers measured body temperature in a sample of 106 adults and found that the sample mean was equal to 98.2 degrees Fahrenheit. And let's say that the sample standard deviation was equal to 0.62 degrees Fahrenheit. And we're just going to assume that the population mean and the sample mean are essentially equal. So we can use that value in our Z formula. Does the sample data provide enough evidence to reject the belief that body temperature has a population mean of 98.6? Because this is the generally accepted value that we think is a typical average mean, in this case, body temperature. Because this coincides with medical research, let's test this with an alpha of 0.01. Let's state our hypotheses. Our null hypothesis is that there are no differences between the common standard, the common belief, that the population mean body temperature is equal to 98.6. The alternative is that the population mean body temperature is something other than 98.6. Remember I mentioned that most tests are two-tailed tests. Theoretically, it's possible that a person's body temperature could be higher than 98.6. Theoretically, it's possible that a person's body temperature could be lower than 98.6. So it makes a lot of sense to do a two-tailed test. That's what's typically done. Well, now let's collect the evidence. We already learned about that evidence based on this study of 106 adults. We know that the sample mean equals 98.2, which at least descriptively is less than 98.6. And we know what we can estimate in terms of the standard deviation, 0.62. So we have all the information that we need to now transform this sample mean into a z-score because we want to consult this distribution of all possible sample means. And we've marked off our critical regions. If we're using an alpha of 0.01, we know that those critical regions are marked off at 2.575 and negative 2.575. This shows where there's 0.5% of the sample means in this tail and 0.5% of the most extreme sample means in this tail. 1% overall. So first we need to compute standard error of the mean. We take 0.62, which is our estimate for the standard deviation, and we divide by the square root of 106. Square root of 106 equals 10.3. If we take 0.62 and divide by 10.3, we should get 0.06. Let's verify that with our calculators. 0.62 divided by 10.3 equals 0.06. So that looks like a good value. Let's go ahead now and take that value for our standard error, which shows us differences between the means that we would expect just by chance, and force that into our z formula. So we take our sample mean, 98.2, subtract the hypothesized population mean based on this null hypothesis, 98.6, then divide by the standard error. So again, what we're looking at right here are the differences that we're actually observing. It's a difference of about 0.4 degrees divided by differences we expect between the means just by chance. So let's verify this value. If we take 0.4 and make it negative, and then divide by 0.06, we find a z-score of negative 6.67. That's a really large z-score. Let me get back here. Negative 6.67. So again, right here in the middle is a z-score of 0. Here's negative 2.575, marking off our critical region, and negative 6.6 is off the charts. It's way deep into this tail. So is it in the critical region, otherwise known as a rejection zone? Yes, it is. So what are we going to do ultimately? We're going to rule out this null hypothesis and take on the alternative, that the population mean body temperature is something other than 98.6. We have evidence to show that it's lower. So let's formally talk about our interpretation of our results in step 4. Our z of negative 6.67 does indeed exceed the critical region, and means that exceed the critical region are very unlikely to occur by chance. So in this case, this finding is likely to occur by chance less than 1% of the time. So in other words, the result is statistically significant at the 0.01 level. So we reject the null hypothesis and we conclude that the population mean body temperature is less than 98.6. So we're ruling out that null hypothesis, rejecting it, and taking on the alternative. Body temperature is less than 98.6 degrees. We can conclude that because our sample mean is less, statistically significantly less than 98.6 degrees. That's a pretty interesting example. All right, let's finally just talk about some errors real quickly. Errors are indeed unavoidable when we're using incomplete information to learn about populations. And when we say we're using incomplete information, we're using sample data to learn about an entire population. We're not going to be correct 100% of the time. So I want you to take some time to look at this table because this will talk about 2 primary types of errors that we can make. We could reject the null hypothesis and conclude that we have statistically significant differences when in fact the null hypothesis is true. So think about the last example. We rejected the null hypothesis and we concluded that body temperature on average is less than 98.6. Well, let's just say in reality, the mean body temperature is 98.6. We'd be making an error, right? Well, in this case, we call that a type 1 error. When we say there are statistically significant results, but in reality there are not, we're making a type 1 error. A type 2 error is essentially the opposite. Let's just say we didn't have enough evidence to reject the null hypothesis. So we did not reject the null hypothesis, and we concluded that body temperature was equal to 98.6. But let's assume that the alternative hypothesis was actually true, and that the true population mean body temperature is something other than 98.6. So in other words, there is a difference. There are statistically significant results, but we didn't have enough evidence to find them. Then we're making a type 2 error. So a type 1 error is when we say we have statistically significant results and we're wrong. And a type 2 error is when we conclude there are not statistically significant results and we are wrong. Well, type 1 errors we have quite a bit of control over because they're capped by our alpha level. So if we have an alpha of 0.05, we can expect to make type 1 errors 5% of the time. That's why there are some fields that aren't happy with that. Like making an error 5% of the time in the medical field might be too much. Now we're talking about life and death types of decisions, about what drugs work, what medical procedures work or not work. So they might say, hey, for us to determine that we have statistically significant results, let's use an alpha of 0.01. The main reason they make that decision, you might have wondered, is because they only want to make type 1 errors 1% of the time. Now only 1% of the time will we conclude that a drug works when it doesn't. All right. The thing that we need to keep in mind is we need to settle on some reasonable compromises because, of course, we don't want to make type 1 errors, but the smaller and smaller we make that alpha level, the more and more evidence we need to find statistically significant results, and that would mean the more times we're going to make type 2 errors. Because eventually you might force me to provide so much evidence that I can't. And thus we're making a lot of type 2 errors. So that's why I say we need some reasonable compromises. And having alphas of 0.05 and 0.01, most people seem to think those are reasonable compromises. All right, I think we talked about enough for this time. That was the key content from section 9.2, and for now, that is all.